Hello lovelies, in this video I'm going to be taking you through my predicted paper for 2023. Now this is for AQA Combined Science Foundation. We're going to be going through this really slowly, so if you've done it already then you can just use this to mark your work, or if you haven't done it already then we can do it together. What I want you to do is to pause the video after the question comes up, have a look at the question, try and write it on a bit of paper and then play the video and work through it with me. Just double check you are doing the right paper. This is AQA Combined Science Chemistry Paper 1. This is the foundation tier. Now I'm going to try and stick to colour coding in this video, so any command words or any bits that are important in the question that you should pay attention to, I'm going to do those bits in blue. When I'm talking to you about the science, when I'm talking to you about the background, I'm going to do those in a couple of different shades of purple. And then the actual answer that I would write down, I'm going to do in pink. I'm sure I will forget my colour coding at some point, and please in the exam just write in black biro. Atoms are made up of subatomic particles, electrons, neutrons and protons. Describe the structure of the atom by matching the subatomic particle to the location of the atom. So we've got to match things up, we've got to draw 3 lines only. They're very clear in bold. If you do more than 3 lines, you won't get the marks. If you do less than 3 lines, you are throwing an easy mark away. Even if you know 2 and you're not sure about a third one, just have a really good go. So there are 3 subatomic particles. We have protons, neutrons, and electrons. And I'm going to colour code them here the same as in my diagram over on the left. Electrons I've drawn as crosses on the outside. Neutrons and protons are the coloured dots that are in the middle. Now the middle bit is called the nucleus. So we can say that protons and neutrons are the nucleus and electrons are in the shells. The model of the atom has changed over time as new experimental evidence arises. State the order in which the subatomic particles were discovered by writing the numbers 1, 2 and 3 in the left-hand column. Electrons are first, protons second, and then it was neutrons. This is something you just need to learn. State who discovered the location of the electrons and 1 tick only. Just tick 1 box, do not tick more than 1 box. Bohr was the person. If you tick more than 1 box in a situation like this, you will not get any marks at all. State who discovered neutrons and again tick 1 box only. The person that discovered neutrons was Chadwick, so we can tick that box. Rutherford wanted to study the plum pudding model of the atom by running an alpha scattering experiment. Describe what Rutherford found and how this changed the model of the atom. So our previous model of the atom was the plum pudding model, named because it looked a bit like a plum pudding, or what we might call a Christmas pudding these days. It was a positive sphere with negative bits throughout all of it. So the positive sphere with electrons scattered throughout all of it. So the theory that Rutherford was testing is that when an alpha particle hit the sphere, that they would all be equally deflected because alpha particles were positive and the positive sphere was positive, well, everywhere. But this is not what's happened. We have a sheet of gold foil here, and this is where we could have alpha particles coming from. Some of them went straight through, which was weird. Some of them were deflected a little bit, and some of them were deflected a lot, which is what they expected to happen. So because we had different things going on, that suggested there was a difference in the different locations in the atom. So we can say this in our answer. Some alpha particles went straight through, some were partially deflected, and some were very deflected or more deflected than others. So Rutherford concluded that the mass, the positive part, was concentrated in a small area. instead of equally all over like in the plum pudding model. And this was the idea of the nucleus. The rest of the atom was actually made up of empty space, which is why the alpha particles were able to go straight through. So we're going to be looking at the mark schemes as well. So we can see that this links up with everything we said: protons in the nucleus, neutrons in the nucleus, electrons in the shells. We get 1 mark for 2 in the correct order and 2 marks for 3 in the correct order. Tick boxes for Bohr and Chadwick. And then we get 4 marks. So some alpha particles are reflected, most went straight through, most of the mass of the atom is concentrated in a small area, which is the nucleus. Ammonia has the formula NH3. Ammonia is a simple covalent compound. There are a few that you have to learn, or you should learn. The formula of ammonia is one of them. There's also oxygen, O2, water, which is H2O, carbon dioxide, CO2. Even if you can't remember them off the top of your head, being familiar with them is always nice. State the bonding seen in ammonia. This is covalent bonding, and again, we need to tick 1 box only. Draw the bonding seen in ammonia, and here we're going to be drawing the outer electrons only. And it is always good to find the things that we're drawing on our periodic table to help us work out the type of bonding and the electrons that we can see in this. So we have NH3. N is going to go in the middle, and then the 3 H's are going to go around the outside. Now hydrogen is over here in group 1, and nitrogen is over in group 5. Now hydrogen has 1 electron on the outer shell. It's in group 1, 1 electron on the outer shell. Nitrogen is in group 5, so it has 5 electrons on the outer shell. We're going to be drawing a dot across diagram for this, so make sure your dots can actually be seen. Teeny tiny full stop just won't be seen. So hydrogen, 1 dot, and then nitrogen, we're going to have 5 crosses. 3 of them are going to be shared and 2 of the same. So nitrogen has 5, hydrogen has 1, but there are 3 hydrogens. So 5 electrons from nitrogen, 3 times 1 lot of electrons from hydrogen makes 8, which is how many we're looking for in an outer shell, except if it's on the first group here, where we just need 2. Compare the behaviour of particles in ammonia liquid and in ammonia gas. So compare, we're looking for similarities and differences, things that are the same and things that are different. We have 4 marks here, so we can generally assume that the examiners are looking for 2 of each. So 2 similarities and 2 differences. So in a liquid or in a gas, we have particles. You can see in a liquid, there's space between them, but they're still pretty far apart. In a gas, they're very far apart and they're all over the place. A liquid has slightly different properties to a gas, and then again different to a solid. Both of them can flow. A gas can be compressed or squashed, whereas a liquid can't. A gas will have bigger spaces between the molecules or the atoms, larger spaces than seen in a liquid. A gas will take the shape of its container, as will a liquid. So there are lots of things here, and we just need to pick 4 facts to write down in our answer. So both liquids and gases can flow and take the shape of a container. However, clearly indicating to the examiners we're moving on to the other part now, gases have larger spaces between the atoms and can be compressed, whereas liquids cannot. Ammonia is a small molecule that is a liquid at -35 and a gas at -30 degrees C. When ammonia boils, bonds break and it turns from a liquid to a gas. Describe which bonds are broken and why, and which ones are not broken and why. What it looks like is a describe. And this is 4 marks. It's asked us to do 4 things. Which one's broken, why they're broken, which ones are not broken, and why they're not broken. So inside an ammonia molecule, we have strong covalent bonds. These are the intramolecular bonds. Between ammonia molecules, when it is liquid, we have another attraction, but this is a weaker intermolecular bond. So we can say the strong covalent intramolecular bonds are not broken. And as we move from liquid ammonia to gas ammonia, it's still NH3. There's no change in formula. So those strong covalent bonds that attach the nitrogen to the hydrogen are not the ones that are broken. It is the weaker intermolecular bonds between molecules that are broken, as they require less energy to. So here is our mark scheme. We get 1 mark for covalent. And then one of the important things about drawing covalent bonding is that this overlapping period here is very clear that the electrons are overlapping, that they are both from the nitrogen and the hydrogen. If you drew them over here, that would be incorrect because they're just in the wrong place. There are lots of similarities or differences. You do not have to write all of this down. That's too much writing to get the marks for this question. That wouldn't be suitable for this answer. But we just picked 2 from each and then got all the marks that we needed to. You did not need to write all of this down. For the last part, we have the intramolecular bonds are not broken because they are very strong covalent bonds. The intermolecular bonds are broken because they require less energy to overcome these attractions. So 2 marks for saying which 2 bonds are broken or not broken, and then 2 marks for explaining the why. Iron oxide is used in industry. An iron oxide can have the formula Fe2O3 or Fe3O2. Determine which has the greater mass. Now this is a 3-mark question, so you're not going to get enough marks to just write down the answer is you have to show working as well. Sometimes in the exam you'll get given the mass in the question, and sometimes you're going to need to know how to look it up on the periodic table, because there is a skill that you're demonstrating in looking things up on the periodic table, knowing which number to look at. So don't always assume that when it's a calculate question like this that you'll get given the number in the question. What you need to look for on the periodic table is in each box we're going to have a symbol and 2 numbers. So we have oxygen and iron, Fe, and there are 2 numbers in each box. The large number, which is generally but not always at the top, and then the smaller number. It is the larger number that is the mass number. This is the number that we're interested in for this question, the larger number. So for the first one, for Fe2O3, and I'm going to put brackets in here because this is how you'd write it on a calculator, we have 2 lots of 56 plus 3 lots of 16, which gives us 160. For Fe3O2, we have 56 times 3 plus 16 times 2, gives us 200. So we can say that Fe3O2 has the greater mass. But you can see that that's actually a fair bit of working out. You wouldn't have just got 3 marks for writing down the answer. Both iron and lithium can form compounds with oxygen to form oxides. State the type of bonding that is seen in both iron and lithium oxide. So here is oxygen, iron and lithium over on the left-hand side. And this line here is the difference between metals on the left-hand side of the periodic table and non-metals on the right-hand side of the periodic table. When you have bonding between a metal and a non-metal, it is ionic bonding. When we have two non-metals, we are going to see covalent bonding. And when we have two metals, we're going to see metallic bonding. Now we can see that iron is a metal, oxygen is a non-metal. When we have a metal plus a non-metal, we are going to get ionic bonding. So we can put a 1 tick in that box there. Now, we need to draw the bonding seen in lithium oxide by completing the dot and cross diagram. So we know that lithium is a metal, so we're going for ionic bonding again. Again, because of the square brackets, we can see that this is what we're being asked to draw, instead of the overlapping that we would see in covalent bonding. Lithium is in group 1, so it will have 1 electron on the outer shell. Oxygen is in group 6, so it'll have 6 electrons on its outer shell. We've been given a massive clue here. We need to get to 8, 6 from oxygen, and then 1 from the 2 lithiums over there on the left-hand side. Now, the electrons that are on lithium's outer shell are going to be the ones that are moved. So we've got 6 crosses here from oxygen, 1 from lithium, and a second one from lithium. The oxygen ion is now 2 minus because it has gained 2 electrons. The lithiums are each plus 1 because they both lost an electron. 2 plus 1, 2 lots of plus 1 and a 2 minus gives us neutral overall. So the first question, we can see that we've done our calculations correctly. We've come with the ionic bonding. And then the second one, I just want to show you the alternative way of drawing this, where all of the electron shells are shown. When I do it, when I've drawn it just for you now, I only showed the outer electrons. So the outer shell on lithium had 0 electrons in it. So that's why I drew 0. When we see here, the inner electron shell of oxygen has 2 on it. Both ways are acceptable. Sulfuric acid is a common solution that is used in the manufacture of fertilizers and salts. Suggest a pH for sulfuric acid. When you see a suggest, it means there are a few possible answers and you need to guess scientifically, use your best judgment to come up with what you think is a sensible answer. So this is our pH scale. We have 1 over on the left, and that is very acidic. 14 is going to be our alkaline, and 7 is going to be our neutral. Now it is sulfuric acid, so any answer here less than 6 is going to be acceptable, because 7 is neutral, so we can't have 7. 14 alkaline, no, anything less than 6 is going to be a good answer. Describe the general reaction by selecting the name of the reaction. So we have acid and alkali, and this is a neutralization reaction. We're only ticking one box. For an exothermic reaction, we're going to have heat given out, and a displacement reaction, just to remind you, is when we see things changing in the halogens or with halide ions. Give an equation for the reaction between the ions produced from aqueous acid and the ions produced from aqueous alkali. So this is just adding things together. So our ions from the question are aqueous alkali here and our aqueous alkali here, and this is a reversible reaction to give us water. When we are doing things in chemical formula, we need to be really careful about the sizes of our letters and numbers. We need a small 2. This is wrong because the 2 is too big. This is wrong because the 2 is in the wrong place. Zinc metal reacts with sulfuric acid to give 2 products, zinc sulfate and hydrogen gas. Write the balanced chemical equation for this. Now, this might seem like it's a balanced equation question, but it's really not. It's just a reading, because we have zinc metal plus sulfuric acid, which they give us here, gives us 2 products, so we need an arrow. Zinc sulfate is one of them, and then the second one is hydrogen gas. So it's asking for the balanced chemical equation, but all it's really doing is saying, can you read this question and then write it down in a chemistry way? There isn't actually any balancing we need to do here. Now we can check this. It's always good to check that you have the same things, same number of things on the left-hand side and on the right-hand side. So on the left-hand side, we have zinc, and we only have one of those. On the right-hand side, we also just have one zinc here. On the left-hand side, we've got 2 hydrogens, and the right-hand side, we've got 2 hydrogens. One sulfur, and then we've got 4 oxygens and 4 oxygens. So this is balanced, and we haven't had to do anything. So while this question might have been a little bit scary because it was asking you to write a balanced equation, actually all you need to do was to read the question. A student tried the same reaction but replaces zinc for magnesium metal. Suggest the products from the reaction between magnesium and sulfuric acid. So again, this is saying you might not know what the answer is, but we think you should be able to work it out from the information that we've given you. So in part D, we learnt that zinc plus sulfuric acid gave us zinc sulfate and hydrogen. And all they've done in part E is switched out the zinc for magnesium. So all we need to do to work out the answer is switch out the zinc for magnesium. So the equation here, and it's not even asking us to write down the whole equation, all it's asking us to do is to write down the products, is zinc being replaced by magnesium. So magnesium plus sulfuric acid will give us magnesium sulfate plus hydrogen. And that is the answer you need to write down. A student wanted to look at the reaction between a strip of zinc metal and sulfuric acid, so the same reaction we've had before. They set up the experiment as shown in the image below. Here is the method. Place a conical flask, that's this shaped flask here, on a mass balance here. Measure out 20 centimetres cubed of sulfuric acid. Measure 2 centimetre strip of zinc ribbon. Add it to the conical flask. Record the initial mass. Record the mass every 30 seconds. Repeat to obtain 3 set of results. So I've just popped this over here so we can see it while we're answering all the questions. Calculate the mean value for change and mass at 90 seconds. So whenever we're looking at the mean, we need to add them all together and then divide by the number of values that we get. But 99.9% of the time, when you see this in a science exam, we need to look out for the anomalous results. This is not maths. In maths, you do it differently. If they ask you this in a science exam, chances are they are looking for the anomalous results. Obviously, there is going to be the exception, but the majority of the time, there is going to be an anomalous result in this. And what you need to do is to find that anomalous result and discard it. So here we have our results at 90, 29, 45 and 31. We can see 29 and 31 are pretty close together. 45 is our anomalous result, so we ignore it. What we need to do is 29 plus 31 divided by 2, because we've got 2 values. So 60 divided by 2 gives us 30. Use the image to help you describe and explain the change in mass. Now in the top here we've got a little bit of cotton wool. So this isn't a bung, it's not stopping things getting out, it's stopping things getting in, so stopping things falling in. So any products that we have, which is a gas, the hydrogen, we know this from the previous page, can escape. So when you see this reaction, we can see that the reaction will cause bubbles, the gas can escape through the cotton wool and the mass will decrease. So the mass is going to decrease. Now I know that's not what it seems to say on the table, but the table is the change in mass, not the actual mass that was recorded. The mass will decrease as gas is lost. Identify a control variable and how they measured it. So a control variable is anything they've kept the same, So the first mark is going to be for what they've kept the same, and the second part is going to be how they've measured it. Now, there are some really obvious ones in the method here. We have the volume of sulfuric acid. In part 2, it tells us they measured out 20 centimetres cubed and put it into a conical flask. You can measure that using a measuring cylinder or a pipette. We also have in part 3 the mass of zinc or the length of the strip of zinc, and you can do that with a balance. So you can have the mass or the length, and you'd measure length with a ruler. Other things that aren't measured would be the concentration of the acid. Now this is going to be the pH of it. We're going to be using the same bottle, but it is not explicitly mentioned. The ones that are easy are the bits that are mentioned in 2 or 3. You can have any of those. So the table showed the loss in mass. Explain why this is not what the student measured. Because it was on a balance, and the balance measures the mass, actually what is the mass at the time, not change. Which is why we need to write down the mass and then work out the change in mass afterwards. Sketch a graph for mean loss of mass versus time. So we need to have our axes and we need to label those. So time is going to be along the bottom and loss of mass is going to be up the side. Now sketch means just draw the axes, the labels and the line. We need to put our units on there, so grams and seconds. We don't need to worry about plotting points for a sketch graph. That's not what it's asking. Now it is going down. This is loss in mass. On our graph, the first bit needs to be fast and then the second bit needs to be slower, as we can see it changing. And you can see I've just drawn the shape of the line here. We do not need any numbers or points plotted. So here we have our answer. So for the first part, any value between 1 and 6. It was a neutralization reaction. Here are the equations that we put in there. And the important thing to remember when you're writing equations is to keep your numbers small. We've got magnesium sulfate and hydrogen. We've worked out the enormous result, but this is for 2 marks. You would still have got 1 mark if you worked out, if you knew how to work out an average, but you didn't notice the fact there was an anomaly in there. And then there are lots of different things you could have put down for the answer to the last part. And then we can say that mass was measured, change in mass is calculated, and change in mass would not be shown on the balance. We need our correct axis, that is label and units, and label and units for the y-axis, and then a third mark for the shape of the graph. Carbon can make a number of different structures. 2 of these structures are diamond and graphite. So here we have our periodic table, and here we can see carbon. First thing, we need to name the type of bonding that is seen in carbon structures. Tick 1 box only. So again, we have non-metals on the right-hand side and metals on the left-hand side. If we have a non-metal plus a non-metal, we are looking at covalent bonding. Non-metal plus a metal, and we're looking at ionic bonding. Metal plus a metal, and we are looking at metallic. So here it is covalent because it's carbon bonding to carbon, and they are both non-metals. Despite being allotropes of carbon, diamond and graphite display very different properties. Now, allotropes is a word you may or may not have come across before, and even if you have come across it, it's one of those tricky ones that might confuse you. So if it is a strange word, don't let strange words throw you off or confuse you in an exam. Some students will see this first word and then will decide to abandon the rest of the question. But if we look at what the actual question says, explain the properties of diamonds and graphite in relation to their hardness and electrical conductivity. So you can still answer this question even if you don't know what the word allotropes mean. And all it means, it's got the same elements in a different arrangement. So here we have some allotropes of carbon that you should have studied in your course. We've got diamond, graphite, and we've got fullerene. Diamond will have 4 carbon-carbon bonds, whereas graphite, each carbon will only make 3 carbon-carbon bonds. Diamond will have a tetrahedral structure to it, whereas graphite, everything is in layers. And these layers can slide over each other, which means graphite is softer because it has layers that can slide. Diamond does not have layers, they cannot slide, so it is very hard. It has a giant structure. And this is a lot that we can write down in our answer. So graphite makes 3 carbon-carbon bonds. 1 electron is delocalized, meaning it can move around and can conduct. Diamond makes 4 carbon-carbon bonds, so there is no delocalized electron, meaning it can't conduct, so there's nothing to flow. Diamond has a giant lattice structure, and its atoms cannot move, so it is hard. Graphite has weaker intermolecular bonds between layers, meaning layers can slide. And it is soft. So we've covered the structure, we've covered the hardness, and we've covered the electrical conductivity. Fullerenes can be made of hexagonal rings of carbon. One example of fullerene is a carbon nanotubule, so a tube. Describe the special structural features of carbon nanotubes that can make them useful in medicine. So in this picture here, the fullerene is spherical, not a tube like in the question, but a ball, a sphere, which means it is hollow and it can fill then with things like drugs so we can send to be where they're needed. A nanotube is a cylinder, but it works on the same principle. It is cylindrical and hollow. That is describing the special structural features that can make them useful. It is saying, what does it look like? If it was an explain question, then it will be asking for the why. So for the first part, we have covalent bonding, and for the second part, we have what is called hierarchical marking. And this is worth spending some time looking over. So for no marks, there are no relevant points made. And these are all the science points that could be included within this. It's not like 6 marks, 6 ticks, writing 6 things. It's much more about we don't call it quality of written communication anymore, but that's what it's like. Can you write a sensible answer? For 1 to 2 marks, some relevant points are made, but it's not coherent, it's not logical, and there's no linking. So for linking, we need to use words like so, therefore, however, whereas. If you've just written down has lattice structure, doesn't conduct for diamond, while those points are right, they're not coherent or logically linked. For 3 to 4 marks, all the points made are relevant, so you haven't written anything wrong down. It is coherent and the points are logically linked. But you might not have covered everything. You might have only talked about diamonds and not graphite. For 5 to 6 marks, it needs to be fully correct, coherent, and logically linked. And the answer just covers both hardness and conductivity for both diamond and graphite. So you can see it is much more than just writing down a 6 bullet-pointed list of 6 science facts. A student carried out electrolysis solution of copper chloride. Give the expected products at each electrode. So we have the negative electrode and the positive electrode. And you can see there are some massive clues on the diagram. On the negative electrode, we can see a solid build-up, and on the positive electrode there are bubbles, which suggest that there is a gas being released. So at the negative electrode, we are going to have copper building up, and at the positive electrode, we are going to have chlorine building. One of the products was chlorine gas. State how you could determine the identity of this gas. So this is testing for different ions. So what we are looking for is bleaching litmus. State the role of the power pack in this experiment. Now we need the power pack, it needs to be turned on so the electricity can flow, or you could say something like to complete the circuit so that there was current to flow. No bubbles of gas were seen. Suggest a modification that would show the circuit had been set up correctly. So if no bubbles of gas are seen, then we can say that the circuit isn't flowing. If we wanted to check the circuit was flowing, we could add a light bulb to the circuit. And some of you might have done this in class to actually check that the bulb went on, to actually check the circuit was working, electrons were flowing, and electrolysis was actually taking place. The students were told to limit the voltage on the power pack for health and safety reasons. Thinking about chlorine gas, explain why. Now, if you ever go to a swimming pool, you might be struck sometimes by the smell of chlorine gas. Chlorine gas is actually toxic. We don't want to breathe this in too much. So to limit the voltage so that we're not getting too much chlorine gas produced, we don't want to harm ourselves. The negative electrode changed mass during the experiment. Describe the appearance of the negative electrode at the end and how the change in mass could be determined. So we're going to be looking at a red-brown deposit here. That's what the colour of copper is. And you could do a change in mass using a balance. But this is a 3-mark question here, so we need to say something else. The change in mass is going to be equal to the mass at the end minus the mass at the beginning. And we're going to be measuring this with a balance. It would be important to do this as the dry mass, so at the end you're not measuring the mass of any liquid that you picked up at the same time. Explain why a solution must be used for electrolysis and not a solid substance. It is because the ions need to be free to move around. In a solution, they are free to move around, whereas in a solid, the ions, the atoms are in a fixed position, so cannot move around. Looking at the mark scheme here, there is nothing extraordinary in this mark scheme, nothing that we haven't said already in the answer. One other thing, instead of a bulb, you could have had a voltmeter to check for the flow, or you could have put an ammeter in there either. Either of those would have been acceptable.
Ouch! This is why in some videos I have unexplained scratches.